FAQ webinar. The topic for today's webinar is monitoring residential wood smoke in BC, and we will discuss why residential wood smoke is an issue of concern in British Columbia, how residential wood smoke impacts air quality in BC communities, and how alternative monitoring methods can help fill gaps in the ability of the current monitoring network to understand spatial variability and wood smoke contributions within BC communities. Our presenter is Matthew Wagstaff. Matthew is a master's student in the Occupational and Environmental Hygiene program at UBC School of Population and Public Health, and he's sharing his thesis project on monitoring the air quality impact of residential wood smoke in British Columbian communities. Because of his work, he was one of the inaugural recipients of the Elizabeth Henry Scholarship for the Environmental Health Research. His research is supervised by Dr. Sarah Anderson and Dr. Michael Brower. Just a few reminders. On the right side of your screen, there is a chat box to pose your question, and we will go over all the questions at the end of the webinar. An evaluation after the webinar. It would be great if you fill it out and provide us with your feedback so we can improve our future webinars. And now I'll pass it to Matthew.
Okay, so hello everybody. Is that working? I'd just like to thank you for the intro there, and I'd also like to thank the BC Lung Association for the opportunity to be here today to talk about how residential wood smoke impacts air quality in British Columbian communities, as well as to share my thesis work to develop a method to monitor these effects. So first of all, I'd like to start by acknowledging that some of the monitoring during the project did traverse the unceded territories of the Lillooet and the Comox nations. I'd also like to thank my thesis committee, starting with my two supervisors, Michael Brower and Sarah Henderson, as well as Arvind Saraswat of the BC Ministry of Environment. Then my thesis is part of a larger project that is funded by the Clean Air Regulatory Agenda at Health Canada. And so I'd like to thank the collaborators on that project, being Nina Dobbin at Health Canada, Scott Weikenthal at McGill, and Natalie Suzuki at the BC Ministry of Environment. Finally, as I already mentioned, the project was funded by Health Canada, but also by the BC Lung Association, and the BC Ministry of Environment provided both site support and equipment rental. So to start from the beginning, why is this work important and why is wood smoke an issue? Well, wood smoke is a combination of over 300 chemicals, and this mixture can vary wildly depending on multiple factors, such as the type of wood being burned, the moisture content of that wood, and then the combustion conditions, such as the airflow and the combustion temperature. And these are mainly affected by the stove technology that is used during combustion. A significant amount of smoke is made up of fine particulate matter, which is responsible for the haze and the reduction in visibility that you see with smoke. And I'll be referring to this fine particulate matter as PM2.5, as it includes all particles which have aerodynamic diameters smaller than 2.5 microns. And the size here is crucial because these particles are small enough to reach deep into your respiratory system when they are inhaled, and some even into the bloodstream. This famous graphic emphasizes the size of these particles, which are the pink here, relative to a human hair and the grains of sand. And this is the component I'll be focusing on, the PM2.5, as it is the most monitored aspect and also the most studied in terms of health effects. So to move on to those health effects of PM2.5, from a mortality perspective, it is estimated 3.5 million global deaths can be attributed to PM exposure each year. But it also acts as a contributing risk factor for many other diseases that affect quality of life. Now, the individual risk may be small from exposure to ambient PM. Because air pollution affects large populations, the overall risk to the entire population is quite high, and research has shown that on days with worse air quality, more people die. So what health effects are involved? Well, first of all, there are clear respiratory health effects of PM2.5 exposure, and these include decreased lung development and function, exacerbation of asthma and allergies, increased rates of COPD and pulmonary fibrosis, and also increased lung cancer risk, and indoor biomass emissions, such as wood smoke, have been categorized by IARC, which is the International Agency for Research on Cancer, as a group 2A exposure, which means they are a probable human carcinogen. There are also many accepted cardiovascular impacts, including higher rates of heart disease, heart attacks, and stroke. In addition to these established effects, there are many other emerging possible health effects, ranging from birth defects and low birth weight to impacts on cognitive function. In addition to particulate matter, wood smoke also contains many other chemicals and pollutants, which I mentioned, such as benzene and polycyclic aromatic hydrocarbons, and these possibly mixed with particulate matter could have additive or synergistic effects on health which are not fully understood at this time. Finally, emissions from residential wood burning are concentrated directly within populated areas, and this is where it can have greater impacts on susceptible populations, such as the elderly, children, and those with pre-existing conditions. So living in Canada, some may compare our air quality to less developed countries and feel that air pollution is not a problem here. But that is not quite the case. So a study in 2015 identified a log linear exposure response relationship between exposure to ambient PM2.5 and health outcomes as a result. They found the response curve between PM2.5 exposure and lung diseases to be almost linear, so that's shown here by the purple line, but they also found a log linear effect for the onset of heart diseases with the green line. The dashed line there is a weighted average of the two types of diseases, and due to the shape of that curve, you can see there's strong effects even at low concentrations of ambient PM2.5, and you can see that due to the steepness of this curve at these low values. So in fact, if we split this mortality axis in half here on the y-axis, you can see that if we reduce PM2.5 from very high levels of around 150 micrograms all the way down to 35 micrograms per cubic meter, we receive a reduction in mortality of half of the axis here. But if we continue to reduce values down from 35 down to about 5, you can see you get exactly the same amount of benefit in terms of the reduction in related mortality. And this is significant because in high-income countries such as Canada and the United States, PM2.5 concentrations are typically hovering in the 10 to 20 micrograms per cubic meter range, and so there is still room for improvement. Specifically here in BC, the current air quality standards are set at an annual average of 8 micrograms per cubic meter and a 24-hour average of 25. Some communities in the province do exceed those standards, and so there remains health impacts which can still be mitigated through further reduction of air pollution, even in relatively clean areas such as here in British Columbia. During the winter months, wood smoke drives air quality patterns in most communities across the province and is often the main source of PM2.5. So why is that? Well, first of all, wood burning is prevalent across the province, and this is for many reasons. It's an available fuel, it's relatively affordable, it's seen as reliable, that you can still use it during power cuts, for example. It's seen as traditional, and it's also somewhat of a renewable resource. Secondly, there's also the proximity of emissions. So typically when you think of a pollution stereotype, you think of a large point source, for example, a big smokestack spewing out emissions. But instead of one large smokestack here, we have many small chimneys directly within the communities where people live. And also due to the geography of the province, many communities are located within valleys, and these have a tendency for inversions to form during the winter and trap smoke. So here's a quick graphic to demonstrate this. Normally air closer to the surface, so in the top image here, is warmer than the air above, and this allows air to rise and mix and disperse pollutants away from the community. However, during a temperature inversion, this is reversed. So this can be due to either the surface area cooling faster than the air above it, which can be common in winter evenings here in BC, or a warmer air mass being blown over the top of cooler surface area. As the surface area is now cooler than the temperature above, this limits atmospheric mixing, and it traps smoke and air pollution in the surface area that we breathe. In a lot of, as I said, most communities are in valleys in BC, and so you can also have hillsides here blocking horizontal mixing, and so this just further amplifies the limit of movement for the air and can really lead to smoke building up over a community. And so just for a further example of how an inversion like that can work, this photo shows a temperature inversion where you can see a single smoke plume, and it rises up until it hits this higher temperature layer, and it can no longer rise any further. And so instead of rising up and away from the community, it actually settles horizontally and drops back over the community and doesn't diffuse away. In 2014 BC Air Pollutant Emission Inventory, residential wood smoke was actually the second highest anthropogenic source of PM2.5 following road dust. Wood smoke exceeded emissions from construction, emissions from industrial sources, as well as transportation emissions from the combination of both ground vehicles and all marine vessels. Obviously here, if you were to include forest fires on this chart, they would no doubt be the largest source and dwarf the scale. But one important thing to note here, compared to these categories of construction, industry, and transport, residential wood burning is effectively unregulated, despite it's a larger source. These other sources have been dramatically reduced over time due to their regulation and new technologies that have been implemented in those fields, but there's been much less action on wood smoke. I'm not advocating for regulation necessarily here, but rather that it should be managed through a combination of regulatory and non-regulatory approaches. So what are some options for how to manage and reduce wood smoke pollution? One option is to pass regulations, and an example of that is the regulations here in BC that have been in place for over 20 years that restrict the types of new wood burning appliances that are allowed to be sold. And that restricts the appliances to more efficient models, and these regulations have actually been recently strengthened. But these regulations do not apply to appliances currently in use. Some municipalities and communities have gone further and passed their own local regulations, and a specific example of that is Duncan, where on a municipal level they regulated that when homes were sold, older stoves must be removed and replaced with new, more efficient stoves. Other possible regulations that could be considered include things such as no burn days when monitored levels are high, that are in place in certain areas in the US. Exchange programs are another option for management, and there's 17 active wood stove exchange programs across the province. This is where users are given financial incentives to help them upgrade their stoves to more efficient models. And this chart from the BC Air Quality website shows the number of stoves that have been exchanged between the start of the programs around 2008 to the end of 2014. So with this data here, it shows there's over 6,000 stoves exchanged for newer high efficiency stoves. But this is the most recent data I have access to. And then finally, education is also a really important aspect of this, because no matter how good the stove technology is that you're burning in, bad burning practices such as burning wet wood will dramatically outweigh that. And therefore, the BC Air Quality website contains tips for choosing and storing firewood, as well as for starting and maintaining your fire in a way that can minimize the amount of smoke produced. A lot of municipalities are hesitant to adopt any new or stricter regulations without empirical evidence to support that smoke is directly affecting their local air quality. So I've mentioned wood stove exchanges, and here's a quick example of the differences in relative emissions between home heating methods. Open burning and simply burning in a fireplace is obviously the least advanced option and produces the most emissions, so that's on the left of the scale there. Then wood stoves contain the fuel and typically burn at higher temperatures and start to get closer to complete combustion of fuel. Newer EPA certified wood stoves have additional features to get even closer to complete combustion, such as recirculating smoke through the fire, and therefore reducing the amount of smoke that is produced and emitted from the stove. Pellet stoves are another good option in that waste wood can be converted to pellets relatively cheaply, and the increased surface area of this fuel then leads to more complete combustion again. The values underneath these two options here may be slightly out of date, as the EPA released new performance standards in the last few years, and these are what the new BC regulations are now based on. The values of these certified and pellet stoves could both actually be lower than is shown here in this image. But even saying that replacing wood entirely leads to further reductions in related pollution, and obviously the cleanest option, especially here in BC where our power is generated through hydroelectricity, is using electric heat for heating. So to move on to monitoring, what is the current situation in BC? Well, the BC Ministry of Environment maintains the air quality network across the province with stations in most of the larger communities. These measure PM2.5 and the criteria air pollutants, including nitrous oxides and ozone, and often climate variables as well. The data is updated and available on the BC Air Quality website hourly, and here's a screenshot just from this morning showing the PM2.5 average of the previous 24 hours. The blue stations are all stations where the 24 hours is below 15 micrograms per cubic meter, and the few yellow stations there are between 15 and 25. and there's no stations in red, which shows none were above the objective over the last 24 hours. I think the yellow ones were only slightly above 15 when I clicked on them, because you can actually see the direct data when you click on these icons. And it's likely, so if you were to look at this map during the winter, there'd be higher values in a number of these communities. And also in the summer, you could see that due to forest fires, especially this year, when we had the worst forest fire season on record. And so there was a lot of red code stations across the province during that time. And this is a good time to mention the key difference here between forest fire smoke and residential wood smoke. And that is that smoke from forest fires is an acute exposure, because despite there being much higher amounts of smoke during the exposure, in typical years, individual communities are only affected for 1 or 2 weeks, while residential wood smoke is a chronic exposure at lower levels, but affected communities can be impacted for the entire winter. So the monitoring network provides extremely useful and valuable data, but there are 2 knowledge gaps that a lot of research is trying to address. Firstly, that there is no routine source-specific information. So instruments are chosen at these sites to monitor the criteria air pollutants, as these are the air pollutants that our targets are set for and that regulations are created to control. The current monitoring data can identify communities with issues, but it cannot provide information on what is potentially causing those problems. Secondly, there is also limited spatial resolution. So from an economic standpoint, it is simply not feasible to install stations in every community in the province. And the maintenance of these stations takes a lot of time, staff, and money. But on top of that, it is definitely not possible to install multiple locations in every community. And so effort is taken to ensure the location of stations is representative of the airspread. But there's always going to be differences across an area, and therefore the measurements of the station may be biased high or low relative to the surrounding communities. This spatial issue is especially important for wood smoke, as it is burned preferentially in smaller communities where they are likely not monitored, and because it is burned in residential areas with small individual sources, there can be a lot of variability within a community depending on who uses or who doesn't use the stove and the quality of the stove that they are using. For example, if your neighbor burns in a poor quality stove or has bad burning practices and produces lots of smoke, you could be a higher exposure compared to someone else even on the same street, and so that variability is very important to monitor. In an attempt to address the limitation of source identification, collaborators developed an algorithm that can use the routinely measured PM2.5 and temperature data and systematically identify smoky days. The algorithm estimates the relative smokiness of a community by looking for common diurnal and seasonal usage patterns which are typical of wood smoke affected communities. This plot is an example of a community which heavily exhibits these 2 patterns. In the plot, the x-axis shows the months of the year, so the winter is in the middle here, and the y-axis shows the hours of the day split into 2-hour periods. Each cell is then shaded based on the relative average PM levels during that month and that time period. So for example, this cell here is shaded based on the amount between 12 and 2 p.m. In December. The hourglass shape of the plot that you can see here, so this is one that is heavily impacted by wood smoke, and so we can see the shape. It's caused by the seasonal pattern where values are higher in the colder months of the year in the center, when heating is necessary and therefore there is more wood burning, as well as a diurnal pattern of darker values in the evening and in the mornings. This is because people are most likely to be out of the home during the day, and then when they come home from work or from being out of the house, they turn on their stoves in the evening, and the values can build up over the evening and last into the morning, and then fade away during the day when they leave the home again and aren't using the stove. And so the usage of this algorithm here, this results allow us to rank and prioritize communities by the wood smoke impacts there. And this not only helps researchers and policymakers to select communities for more focused sampling studies such as our own, but it also helps with emission reduction strategies. And it can also be used to inform at-risk municipalities with objective evidence of wood smoke impacts. And this could lead to increased public and government interest in enforcing the adoption of cleaner residential heating technologies. While this is a useful complement to monitoring data, it is still limited in that it can only be applied to communities that already have monitoring stations. In terms of an option to measure and identify empirical evidence of wood smoke pollution in the field, The most extensively used option is levoglucosan analysis. So levoglucosan is a chemical marker of wood smoke that has been used extensively and is seen as kind of a gold standard for measuring wood smoke. It is a sugar anhydride that is derived from the pyrolysis of cellulose during biomass combustion, which more simply means that it is emitted when wood is burned at high temperatures. And it is useful because it's emitted in high concentrations and it is relatively stable in the atmosphere. And this allows it to be captured and therefore measured. But the problem is this is an expensive process. It requires collecting samples on gravimetric filters over at least 24 hours, and then expensive lab analysis to quantify the amount captured on the filter. So while it's a useful technique for collecting more data on the source of PM2.5, it's not feasible to use for large-scale spatial monitoring projects because of the large associated expense. In terms of addressing that second knowledge gap of a lack of spatial resolution, mobile monitoring is one option to collect spatial data. Typically, this consists of operating continuously reading nephelometers, which are instruments which provide a real-time estimation of PM2.5 in a vehicle driven on a predetermined route, and then matching the data from the instruments with GPS location measurements during the drives. If you are interested in monitoring wood smoke, you can then target the times that you conduct these runs to times when you expect wood smoke to dominate, and therefore conduct the monitoring during late evenings and night times. So some previous examples of mobile monitoring in British Columbia include some work by our research group in Greater Vancouver in 2007, which is here on the left, and then some University of Victoria monitoring in the Comox Valley in 2009 on the right. Our group also conducted mobile monitoring in Smithers in the Bulkley Valley before and after a wood stove exchange program there to evaluate the effect of upgrading stoves, and that data is currently being analyzed, ready for publication. Okay, so now it's time to introduce my own project, and so we created a method to target these two knowledge gaps by combining mobile monitoring using a nephelometer to address the spatial resolution, installing an anephalometer to provide more source-specific data rather than a simple PM2.5 mass estimate. Additional instruments were also co-located next to the monitoring station instruments to complement and compare them, and gravimetric filters were collected to be analyzed for levoglucosan. I tested the method in 3 communities, and these were identified as being impacted by wood smoke using the monitoring data and the wood smoke algorithm that I described, as well as 3 nearby unmonitored communities. So I mentioned 2 instruments there. Both the nephelometers and the anephalometers are continuous monitoring optical instruments. They can both be used in a mobile monitoring setup. And in the past, we've only used the nephelometer for measuring spatial patterns of particular matter. But for this project, an anephalometer was also used to add more data on the source of particular matter. So how do the 2 instruments differ? Well, a nephelometer, first of all, draws air through a sealed dark container. So this image here is the interior of the instrument, and you can see the long dark tube here. So the air sample is drawn into that tube, and then a light beam is shined through the air sample, and sensors measure the amount of light scattering caused by particles in the air. The amount of light scattering is well correlated with the concentration of PM2.5 in the sample, and therefore this provides a real-time estimate of PM2.5 in the air. The anephalometer differs in that it draws air through a size-selective inlet. So first of all, it filters out anything larger than PM2.5, and then deposits that PM onto a quartz filter tape, which are the dark bands seen on the tape on the inside of the instrument here. Then once every second, the instrument shines multiple wavelengths of light through the filter tape with the sample and measured how much light at each wavelength is absorbed relative to the last second. When the sample spot on the filter tape gets too dark, the filter moves on and starts in a new clear section, and that's why you can see multiple bands. The key difference between the instruments is the anephalometer has the multiple wavelengths, and so differences between the amount of absorption at each wavelength can then tell us a lot more about the chemical composition of the sample, rather than just the total amount of PM2.5. And so to clarify how the differences between wavelengths give us more information on the source, this graph is from a recent paper by a group including George Allen in Boston, who pioneered a lot of this work developing the use of anephalometers for measuring wood smoke. The anephalometer measures light absorption on a quartz filter tape at multiple wavelengths, and these are depicted by the color lines here on the charts. but we are specifically interested in the 880 nanometer band, which is called BC and measures absorption by black carbon, and the 370 nanometer wavelength band known as UVC, which measures ultraviolet absorption. So that's the red line here and the gray line. The difference between these two wavelengths is known as delta C, and that has been shown to be a good indicator of wood smoke. And the reason for this is because PM from biomass combustion contains much more UV absorbing compounds than PM from other sources, such as traffic-related PM. These two plots show the instrument's responses to two different sources. So on the right, this plot shows a test using a diesel generator as a PM source, and there's very little difference in absorption between the wavelengths, and the lines are effectively on top of each other, so you can't see the different colors here. But in the plot on the left, the instrument is measuring wood smoke PM, and the UV band is significantly higher than the other bands, and the difference between the red and the gray line, which is down here by the black, is known as delta C, and that can be quantified. So the blue arrow here is what we are measuring, and these sections is when there is a plume of smoke to be measured. So here's how our vehicle is set up for mobile monitoring. The two instruments in this case were installed on the rear seat of the vehicle, where the air inlets pass through the rear window and attached to the side of the vehicle. The inlets were attached to the side opposite to the exhaust to limit any effect on the PM measurements by the vehicle's own emissions. And then a GPS is installed on the dashboard to collect the vehicle's location throughout the monitoring bands. And then here's a photo of the fixed site in Whistler. So there's a lot of snow removal required during this monitoring. The white housing in the center here contains the Ministry of Environment equipment, and the air intakes are on the top of the housing here. Then on the right, you can see the black Pelican case, which is containing a nephelometer. And then another Pelican case is hidden under this blue tarp, and that contains the athelometer with the air inlet attached to the side of this housing here. And then in addition to these two instruments that were matching the instruments in the mobile monitoring vehicle, the wooden stand here is also holding two Harvard impactors, which were used to collect gravimetric filter samples each day, and then these were to be analyzed for level glucosone. To choose the communities where we would test the method, we use the Woodsmoke algorithm work that I mentioned to identify the communities of most interest. So here are the communities in the province that are ranked by the smokiness determined by the algorithm, and you can see that that hourglass pattern that I explained is pretty clear in the first few examples, and then kind of breaks down as you get further on. And we picked 3 monitored communities from different regions of the province for this monitoring campaign and to test this method. The first was Whistler, and this was chosen for its proximity to Vancouver, as well as the interest in the area. And then Pemberton was chosen as the nearby unmonitored community to go with Whistler. Courtenay was chosen as the Vancouver Island community that has a lot of current interest in smoke levels, along with a nearby Cumberland as the unmonitored community there. And finally, Vanderhoof was chosen over Houston as a northern community, as there's been some previous mobile monitoring in the area around Houston, and there was no nearby unmonitored community to pair there. But there was interest in collecting data on both Vanderhoof and Fraser Lake, and so they were chosen as the final pair to monitor. So in terms of the monitoring campaign itself, routes were first pre-planned with some community feedback, and then I had a GPS device giving me directions throughout the monitoring, so then it was easy to repeat the routes exactly. Each community pair was monitored for 2 weeks over January and February 2017, with monitoring runs performed each night to target the times when wood smoke is expected to be the main PM2.5 source. The 2 paired routes were alternated each night, and this is to limit any weather differences between the routes. For example, if we had a cold spell, it would hopefully impact both of the routes equally. And then routes were also driven in alternating directions to limit the effects of temporal patterns. So you don't want to always monitor the same spot at the same time of the evening. So since the campaign, I've done a lot of data analysis, but to quickly explain how I produced the maps, I'm going to present just the steps for the mobile data. First of all, the data was cleaned, and the mobile instrument data matched to the GPS coordinates. The frequency distributions for each trip were log normal, so there's an example here with the blue distribution curve. And this is to be expected when environmental data has a 0 value. The data was then normalized by taking the logarithm of the data, and this is necessary to allow the data to be converted to z-scores. This is a method we chose to extract just the spatial patterns from the trips and therefore allow us to average the patterns between trips. So if anyone who's not familiar with z-scores, a z-score is the number of standard deviations a value is away from the mean of the distribution. So if you compare the red distribution here, which is after the normalized transformation, to the green distribution below, you'll see the distributions are exactly the same, but the x-axis has changed, and so now the mean of the distribution has a value of 0, and approximately 95% of the data falls within 2 standard deviations of the mean. So for example, a value of 1 would fall here and be equal to the mean plus 1 standard deviation. After each record had a location and a z-score assigned to it, a raster grid was then created to cover the monitored area with 33.3 square meter cells, and then measurements that were recorded within each of these cells was then averaged. And the raster grid was then focally smoothed, meaning the surrounding cells were used to adjust the values, and therefore each cell is a weighted representation of the measurements in a 100 square meter area, and that's the rasters that I used to produce the maps that I'm going to show. So time to talk about some actual results of the project. First of all, here's a quick overview comparison of the communities from the gravimetric filter measurements at the filter sites, at the fixed site, sorry. There's 14 data points for each community over the 2 weeks, with the 24-hour PM2.5 concentrations on the x-axis and the level-glucosan concentrations on the y-axis. There's very high correlation in both Whistler and Courtney, which is the blue and the red lines here, and that's shown by the high R-squared values. And this suggests Woodsmoke was the dominant source of PM2.5 during the monitoring period. In each of these communities, approximately 10% of the total PM2.5 on the filters was identified as level-glucosan. The relationship in Vanderhoof, which is the green line there, has both a lower correlation and slope. And one explanation for this could be due to the large amount of road dust that was present during the monitoring period. So while I was there doing the monitoring, the snow had just melted on the roads, and this is when a lot of traction material that has been laid on the roads over the winter can get kicked up by traffic, and so there was a lot of visible road dust that was likely affecting PM levels. Now, when comparing the two Woodsmoke specific methods, there is very high correlation between the delta C measured by the athylometer and at the fixed site and the level glucosan measurements in each location. So you can see the lowest R-squared value at any of the sites was 0.945, which is very high. And so this validates the use of the athylometer compared to level glucosan as a gold standard, and is evidence that the instrument is actually measuring wood smoke. So that was good for us to see. However, this relationship is not consistent between communities, as the relationships were very similar in Whistler and Vanderhoof. So these blue and green lines here are almost on top of each other, but the slope was much higher in Courtney, and so this kind of raises some questions here. So even though level glucosan is treated as the gold standard, the amount of it that is produced during combustion can vary based on factors such as temperature, wood type, and moisture content. So something else could be going on here that is causing these effects. So this slide shows a good example of the differences between the two instruments during the mobile monitoring. The plots are from 2 mobile trips, and there's no y-axis scales included, but both plots were plotted on the same scales for each instrument. The left plot shows a time series of a daytime monitoring run in Fraser Lake, and so that route had a lot of highway sections, and as I mentioned, there was a lot of visible road dust during the campaign there. And so when these large road dust spikes were seen, the black line from the nephelometer jumps up and responds to the PM2.5 from that source, but the athylometer, which is the red line, recognizes that it's not wood smoke, and so the delta C is effectively 0 at that point, and there's no response from the instrument. The right plot shows the monitoring run on the following evening, and so during this run there's probably less traffic on the road and less road dust influencing the results, and as a result there is high correlation between the instruments throughout, as wood smoke is more likely to be the dominant PM2.5 source at the time of that monitoring run. Okay, time to show some of the maps. Here's 2 maps showing the nephelometer data for the first 2 trips on the Courtney and the Cumberland route. So the raster cells have been categorized and shaded based on bins of z-scores that are 0.5 z-score wide, and corresponding PM2.5 estimates were calculated on the legend for comparison there. So any area, for example, shaded in this orange color here is between the mean and half a standard deviation below the mean. These maps show you the amount of variability that exists across the region within each trip, and you can clearly see that certain areas are much darker or much lighter than other areas. As well as this, there can be a lot of variability between the trips, and for example, lower levels were measured in the north corner here on the first trip, but then higher levels measured on the second trip. And so because of this, this is why we repeated each route 7 times in alternating directions, and then averaged the results across the trips to get our final maps. So here's the first of the route pair comparisons. The maps show the average z-scores, and so the PM estimates in the legend here are only for the 9 hours during the routes, when the routes were driven. The highway data that was measured between going to and from Whistler to Pemberton was removed from the Pemberton route prior to calculating z-scores, as these very low levels there would bias the relative score there. And as a disclaimer, first of all, this data is only from 7 trips in each community, but it does begin to draw out reoccurring patterns. There's few homes on the west side of the lakes in Whistler here, and as you would expect, then there's lower levels measured during our monitoring. There's also very low levels measured in the Olympic Village area, and that would also be expected as there's very new homes there and very few stoves. Conversely, there's hotspots to the west of the monitoring station, which is also to be expected. This is an older area of the community, and therefore more wood stoves in the area. Pemberton, meanwhile, is unmonitored, but hotspots were still identified throughout the community, especially in southeastern Pemberton and around Mount Curry. And the monitoring station itself is located here at the blue circle, and this fell almost right on the mean of the 2 routes during the monitoring days. So it had a z-score of 0.01, and this is the station appears to be doing a good job of showing the average exposure across the 2 routes. However, this kind of highlights the importance of the spatial variability. So even though this is picking up the kind of the average exposure, there's big differences from one end of the community to another end. So here's the Comox Valley data, where the 2 routes were split by the Courtenay River. The left route covered the west of Courtenay and Cumberland, and the right route covered east of the river and Comox itself. As in all pairs, both routes started and finished at the monitoring stations, so the routes could be compared. And then for those unfamiliar with the area, you can see the right map fits to the northeast of the left map. So the station is here on this map and here on this map, and you can use these 2 ridges here to identify how the maps fit together. Typically, much higher values were seen while I was monitoring this region than while I was in Western Pemberton. And there was actually 2 air quality warnings during the monitoring period, so this is kind of worst case scenario. While the routes were alternated each night to try and ensure as similar conditions as possible, the Ministry of Environment and Equipment recorded average PM2.5 concentrations of 31 micrograms per cubic meter during the nights of the Courtenay and Cumberland route, but only 21 micrograms during the nights of the Courtenay Comox route. So that's quite a big difference between the 2. And so for that reason, I left the routes separate here, and this should be considered when comparing the PM estimates there in the legends. Again, these maps are from 7 nights, but are a good approximation of the patterns across the valley, with the Courtenay and Cumberland route showing hotspots in southeast Courtenay as well as northeast Cumberland, and the Comox route showing hotspots around the monitoring station in the main residential area of Comox and in the northwest of the route. So in the station here in Courtenay, around the more densely populated area of Comox, and then up here as well. So Cumberland is an unmonitored community here, but there was relatively high levels measured, and there's quite a lot of variation across that community, so that's interesting with the method. And the monitoring station in this area is in Courtenay, and this fell higher on the distribution of the routes compared to the Whistler and Pemberton situation. So it had a z-score of 0.44 during the Courtenay and Cumberland route nights, and a z-score of 1.4 on the Courtenay and Comox route relative to that route. And so it's a little bit higher than the average of those routes. But for example, this route had some more rural areas, and you remember that the z-score is relative to where the route is drawn. So here are the Vanderhoof and the Fraser Lake patterns. along with Fort Fraser, which was included on the Fraser Lake route. The main image shows the entire Vanderhoof route, but the Fraser Lake route consisted of long sections of highway driving, so these were all removed prior to calculating Z-scores, and only the populated areas were mapped. The more densely populated areas seem to show the higher Z-scores, and these maps you can see the hotspots in the northwest and northeast of Vanderhoof, as well as in kind of western Fort Fraser here and the north and west of Fraser Lake. Data around the monitoring station was interestingly lower than the surrounding area, with a Z-score of negative 0.9. This may be a result of limited stove activity around that station, as it's next to a high school with a large field and commercial buildings which are all closed during the evenings when this monitoring was done. Therefore, this is potentially a good example of where the station data may not be completely representative of what a lot of homes in that area are exposed to. So to kind of conclude on the method, we found the method is able to measure spatial patterns in a region and complement the data from a monitoring station. It is relatively quick and efficient to apply and is able to identify hotspot areas in communities. The resulting maps from the data can be used to prioritize areas for targeting exchanges and could also be combined with further research of health effects, for example. The method is also a quick option to characterize unmonitored communities at little cost. And in terms of the Woodsmoke findings, we found high correlation between the two instruments overall during the night mobile runs. And so this adds evidence to support the residential wood smoke as the dominating source at PM2.5 during these winter nights. Finally, this can only be considered semi-quantitative data, that being the mobile monitoring data, and that's because this method is limited by the fact that we are not able to monitor everywhere simultaneously, which would be the hypothetically ideal situation. Therefore, effects of other variables are introduced in when each area is measured. And methods such as Z-scores are also limited as they're only relative to where you draw the route, and so you have to be careful with how you draw it. However, given those limitations, the method does the best we can to draw out patterns and reduce some of those limitations by, for example, monitoring on multiple nights and averaging out the different conditions. Other methods could then be attempted to address the limitations of Z-scores, for example, using models to extrapolate the data between sections of the route and try and cover the community more effectively. And some takeaways and next steps. So to kind of wrap this up, mobile monitoring is able to provide highly resolved spatial data, and this can complement existing monitoring and identify hotspot areas that can be used to target improvements such as exchanges, etc. The correlation with levoglucosen has shown the atherometer is highly correlated with wood smoke, and the relationship with the nephelometer shows that wood smoke dominates these communities during the winter periods. These results have been presented to the communities to inform them of our findings and so that the data can be used for local developments. And the equipment and method will be made available to be used in other communities around the province in the future. And so I'd just like to thank you all for your time today. I'm happy to try and answer any questions that you may have now. I've also included my email here for any questions you have later on. Okay, so some of the questions here. The first one is, according to news reports on Metro Vancouver wood stove rules, Julie Sexton was quoted saying, anyone who bought a wood stove within the last 25 years will probably find that it meets modern emission standards like those proposed by Metro Vancouver. Is this true? I would find that that's probably true. So as I mentioned, BC has regulations in place for the last 20 years. And so that has limited all stoves sold in that time to be stoves that are certified by the EPA to be lower emissions. And so any stove bought in that period of time will be one of those stoves. So I would say that's likely true. The second question is asking, will this monitoring project include a component to address the acute issues associated with forest fires? That's not something that this project is looking at. This sort of equipment could be used in that sort of situation, but that is a different exposure, as I mentioned, and it would have to be able to react much more quickly to when the exposure happens. But it could be used to kind of map that. But the issue with forest fires is they change very quickly. So we're able to monitor like the average patterns over a winter because it's happening every night. But as soon as the wind changes with a forest fire, the smoke can change quickly from one side of the community to another. and so the maps may not be useful there. The third question, in terms of relative emissions, in terms of the relative emissions chart, so that was the one I showed, do you know if the green bubble for EPA stoves is based on certified ratings or on actual use studies? Is it clear from lots of research that actual use is far higher than certification? Sorry, it is clear from lots of research that actual use is far higher than certification levels in most cases. So even with new regulations, the relative emissions will still be far higher than gas or hydro. This raises a kind of a tough question here. So these stoves are going to have much lower levels than older stoves, and so it's a drastic improvement on continuing to burn an old stove. And that's why I mentioned as well the importance of education. If you have bad burning practices, that can obviously lead to more smoke being produced in actual use, as you mentioned. But that's why education is important, to try and encourage people to burn correctly and limit the smoke produced. But obviously, as you mentioned, like gas or hydro is going to have lower levels, but there's limitations to what we can do. So the fourth question here is, have the low-cost Purple Air PM2.5 air quality monitors been evaluated as to the accuracy and usefulness? Many BC communities are now installing these monitors. So I know there is some research looking into all these new monitors that are coming online. There's lots of different brands and lots of different companies producing monitors like this. And there is research looking at them, but they're never going to be at the same level as monitors that are maintained by an organization such as the Ministry of Environment. If you install one of these monitors and just leave it running, no one knows how well it runs over a long time. So there's a lot of questions to answer there, and how accurate these are. They're usually at a much smaller device and have much less sophisticated technology to measure these values. And so I'd explain some caution with the results from those monitors, but they could be useful if they are proven to be accurate. And the fifth question here is, will the individual maps from each night and monitoring be available in the final research? And so yes, that's what I'm currently working on, putting my thesis together, and so I will be including maps from each night, and so that could be seen in the final product. But the limitation with individual nights is there can be a lot of variability, as I mentioned, and so the whole reasoning for doing this and repeating it up to 7 times is to try and avoid and remove that variability. So putting too much emphasis on a single night run can be flawed. On the Comox Valley maps, you have the PM2.5 equivalent for the Z-score of 1.5. What is the PM2.5 equivalent for the Z-score of 2? Can we get that information, as it clearly is not an equal jump for every 0.5 of the Z-score, so people living in these areas above Z equals 1.5 can't figure out the range of their exposure. And so yeah, that's a good point there. A Z-score, as I said, is a standard deviation difference, so it is increasing by the same amount, but it's hard to see that because it can be quite a difference there. Yeah, so I haven't included that on this map, so I don't have it offhand, but that can be, I can add that in the future. I do know levels were up to, I think it was 4 times higher than the mean on that run. So that would be the highest value there. The next question is there a way to integrate the 2 maps across the Comox Valley, as it is confusing for most to look at and see the same colors and understand the scales are different? And so this is something that is kind of the reason why this has taken so long for me to do the analysis of this data. There's a lot of variables affecting this, and this is the best way we've found to try and limit that and present this in a fair way. If you were to match the two routes together, they were monitored on different nights, and as I said, despite us trying to avoid that by doing the alternating nights, there was still quite a big difference in conditions. So during the Cumberland one, the conditions were 31 average PM value and 21 during the Comox route. So this is quite a big difference. So if you were to compare the 2 routes, that wouldn't really be fair, other than to do it in this way. So just looking at the relative patterns and using the monitoring station there as a way to to compare the two routes. But that's all I can really say at this point. It is difficult to do, and in an ideal situation that you'd be able to do that, but unfortunately there are drawbacks. The next question is, are PM2.5 concentrations hourly averaged or instantaneous? And so I don't know what you're referring to that question directly. I know that the PM2.5 concentrations reported by the Ministry of Environment Equipment are hourly averages, and you can access those almost immediately after the hour, every hour. They also report 24-hour averages as well, and then the annual average is looked at for regulation reasons. In terms of the instantaneous ones, the ones from the instrument I'm using is effectively instantaneous. So the nephelometer takes a measurement every second, and as I'm driving, say I'm driving at 35 kilometers an hour, that's roughly one measurement every 10 meters, I think it was when we worked it out. And so each of these routes during the night, there's 100,000 measurements on those routes. So there's a lot of data that's averaged into these final maps. Next question is, older EPA certified stoves degrade over time according to even industry people. A stove with a catalytic converter will operate as poorly as an uncertified stove if the converter is not changed every 4 to 5 years, and other stoves also degrade. So this is not something I'm personally familiar with, or I don't think capable of answering. So I'll leave that up to someone else to answer on that one. How can or will these results be translated into public communication on residential wood burning? So I put together some short overview reports of these results that I've sent to people in the communities. Hopefully they can be used to inform local decisions. In terms of future work, these instruments could be used in other communities and create similar maps. And hopefully, yeah, the best case for this is being used to inform decision making, and then hopefully, like, we have more educated decisions when these decisions are made. Got one more question. The bottom there. Okay. So from a community monitoring perspective, with a single site to represent air quality in a community, do you feel it's better to have a Z-score closer to 0, or is it better to have something between 0 and 1.5 to ensure the monitoring site more likely represents what the broader community is being exposed to? This is a hard question because it kind of refers to who you're trying to target. So the average, so for a station to represent the average with a Z-score of 0, then shows you what the average exposure of the community is, which is ideal from that perspective. But then again, as I said, there's a lot of variability, and so like you mentioned, a higher Z-score would show that the people who are exposed to higher levels, kind of include them into this. But it's hard to say which one is more important. Like, I think both are important, and so for that reason, I would struggle to answer which one is the best situation there. The comment about stoves degrading was in response to the question from the person about the article on the Vancouver Sun. You claim that 25-year-old stoves will be EPA certified and therefore have lower emissions. This is not true in all cases. Well, I guess the 25-year aspect, the ones right at the start of that 25-year could be non-emission if they were before the regulations were passed. But any stove that has been sold since the BC emissions came into force are all lower certification stoves. And these have been improved over time. So as I mentioned when I was showing the relative emissions, the EPA certifications have improved, and as a result, the BC levels have also improved. So that is changing over time. This question is the information you developed from your results and sent to the community available online? Thank you. So I've actually just sent these community reports out this week, and then we'll be deciding how they're made available. I don't think that's my decision to make, but we'll see how they're made available for people to access them.
Okay, so thank you everyone for listening, and just a reminder again, please remember to plot the evaluation that we will send you today following the webinar. Thank you and have a great day.